Okay. Okay. Hi, everybody. This is Professor Ma, and this is the introduction to the sections on conic sections. Okay. We start with the difference between graphs of functions versus graphs of equations. In the form of functions, we can write put put these into the format of y become a formula in f of x. And then we get a graph on the left hand side. And they are functions so that every vertical line, there's only one point in the set of pictures. Now, when we come to this side, talks about the graph of equations. The equations is a formula with x and y all mixed up. And these are a couple of simple ones that involve y squares that you cannot solve in terms of y functions. And then you get these curves that can double back on itself. These are not functions because if I draw a line, a straight line, the 2 points over here corresponding to a single x. So it's not, they're not pictures of functions. And we're going to look at, okay. Sorry about my videos. It's having trouble with the cameras on it. And so let me just stop the videos. Okay. Continue. So let's talk about first degree equations have been run through many times. These are straight lines, and they come in two types. So one type is that they are functions, the other type is they're not functions. So so this is if y is there, then we can solve this as a function, and we get these two types: positive slope, slope 0. Okay, and then if y disappears, turn y, so we can put into a function, we get vertical lines. Okay. Then the next case is what we are going to investigate is a second degree equations between x squared and y squared. Okay. And the pictures that these equations produce are called conic sections. And they are so, it is so is because the pictures correspond to the exposed, the cross sections of a cone. One way to study solid is to cut through the cone and cut through the solid to look at the cross sections. Okay, and so these are the cross sections of a cone. So there are four basically. If we depending on what angles we take the cross sections, we get four different types. And if we cut parallel to the ground, then the exposed the areas, the circles, horizontal sections. Okay? If we tilt the cut angle slightly, so it cuts off the tip, but at an angle, then the exposed area is a stretched circle. Okay, and it's ellipse. So if you tilt moderately, then we get this compressed or stretched circle. These are ellipse. Okay, then if we cut just parallel, oh, by the way, these two cuts, the exposed cross sections are closed. Okay, but if I cut parallelly to the edge of this cone, if I cut parallelly to this side, so I get these, then I'll be slicing forever, and there wouldn't be a tip that can slice off. It's just a real long slice parallel to the side, and then what it exposed is a parabola, excuse me, and we went through that already. And that's basically one special case of the second degree equations. Okay. Now, suppose if I cut away from the halfway mean, so this is a parallel to the edge. Now, suppose I cut like that and slice out the corners over here. Then what is exposed is a slightly different type of, it's a different type of curves. They're called hyperbola. They kind of shape like parabola, but they have a lot sharper, pointy vertex. Okay. So these four types of curves corresponds to these second degree equations that we just we have shown right here. These set of equation here. And how do we identify which type is which, and how do we graph? Given what's the relationship between the second degree equation and this different type? There are four different types here, and how do I relate the equation to four different types? And this is what we're going to do. And it turns out all the algebra are based on one tricks, okay? Here's a summary of the four different types, okay? And in particular, we are not graphing this equation, the tilted versions. We are graphing the ones that are basically parallel to the axis. Okay. If I throw in the term x times y in here, plus xy, say, okay, x times y, then what's happening is we'll be tilting the graphs, but we're not doing that. And also point out, it depends on what coefficient I have A, B, C, D, and then I get these kind of strange cases. Okay, they might be just degenerate into two lines. It might be just a point. It might be no graph at all. Okay, so we're not talking about these things. So in general, I will get from these equations these four different types of graphs. How do we differentiate them? And it turns out that it's based on two different ideas, one from geometries and one from algebra. And the geometry basically is that all these second degree equation basically came from something related to distance. We'll see how that's done. And then the algebra, to relate the distance formula is we call it completing the square. And it is the most important single one trick for solving second degree equations. Okay, and that enables us to solve all second degree equations. The quadratic formula came from that. Okay, so we will do that from both. Okay, so we're going to learn the completing the square trick from the algebra part. Okay. And we also need the distance formula from the geometry. Notice the distance formula has something to do with squaring. Okay. And let's look at a case of circle. Okay, and the circle in mathematics, the set of all the points that have the same distance to some center. Okay, so the red points, two red points have the same distance R to the center C, and a lot more points there. So if I finish drawing all the points and they form a circle. Okay, so this is the mathematical definitions of a circle. And suppose I know the coordinates of the center of the circle, HK, then from the distance formula, since the XY let's say XY is the general point on the circle, then the distance from XY to center HK is R. And these I can write using the distance formulas, the U achieving is these. And what we have, plugging these statements precisely says the distance, distance between XY and HK. And then the answer is supposed to be that equal to R. And so that's what this equation, therefore, is the equation describing this particular circle. We call this the standard form of the circle equations. Okay, why? Because if we have the formula in this, then we can format. Radius is identify what the circle, what the radius is R, and where the center of the circle is centered at the point H and K. Okay, and let's notice that we have to have the how we identify these equations. Okay, first of all, the equation that you have to have minus sign there, and the R is going to be the radius, and HK is going to be the centers. Okay, so for example, and so if I want to write down the equations of these equations, and we identify the center is -1, 3, and the radius, I just count 1, 2, 3, 4, 5. So I can write on the center and the radius, and then I can put these numbers into the H and K, and R is 5, and then voila, this is the second degree equation for this circle. And here's another examples. Okay, in these examples, we have the equation, we identify the geometry. That's where's the center, what's the radius, and it's easy to eyeball. Oh, the radius, the center, radius 4, and the center is at 3 and -2. Okay, this is negative sign, and that I can plot it. Okay, I can, here's 3 minus 2 and 4 distance 4 out the 4 out, and so we plot those 4 points and then complete the circles. Okay, and now what happens if I have a general equations that's not in the standard form? Okay, then this is where the algebra comes in, is that any second degree equation can do a trick called completing the square and put into a square form, which is somehow related to distance. And this trick is called completing the square. And here how it goes. Okay. Let's say we have x squared minus 6, and I want to put in the box a number to make this a square formula, and then the trick is take half of the numbers middle terms over here, minus 6, and half of that is square that and put in the box, okay, which is 9. If you put, if that number is 9 there, then this will be a square of a monomial. Same thing with the bottom one, second one, I take the half of 12, 6, square that is 36, and so this will be y plus 6 squared. So what we're going to do is we're going to have a, for example, here's how we complete the square of these equations. Okay, so this is the equation of a circle, but it's not in the standard form. So what I'm going to do is I'm going to put them into x something square, y something square into the standard form to read out the centers in the radius. Okay, so how do we do this logistically? Well, first separate the x's into one group and leave a parking space because I'm going to put a number there. Okay, same thing with the y's, and group them, okay, in orders, y squared plus something, and leave a space over there and move the numbers to the other side. So you put them into this format. Now, I'm going to complete a square for the x's. So take half of a minus 6 and square that is 9. So I'm going to add 9 to the x's. And since it's the equations, I have to add 9 to both sides to make these steps valid. So I'm not changing the equations. And this completes the x spin square. It is x minus 3 squared. Okay, and then I do the same thing with the y. And this is, remember, we have plus 36, so we do plus 36, and then this becomes a y plus 6. And they are joined by the plus. That's how we complete the square. The symbol with x and y side. And the right hand side, we'll just keep track of the number. So, and that's of course 3 squared. And that is the standard form of the circle. From here, I can read the centers of as 3, -6, and the radius is 3. And from there, I can graph. I know what the picture looks like. Okay, and that's it. Do the homework, and bye-bye.